Okay, class, this chapter is chapter 19 on chemical thermodynamics. Now, you remember in chapter 5, we talked about the first law of thermodynamics. Energy cannot be created nor destroyed. Therefore, the total energy of the universe is a constant. Energy can, however, be converted from one form to another or transferred from a system to the surroundings or vice versa. Now, we got two things. We got delta H and delta S. Delta H is enthalpy. That's the heat absorbed by a system during a constant pressure process. You got delta S, which is entropy. And entropy is the measurement of the randomness of a system. Now, I'm going to write that here. That is delta. I can't write that well with this. And this is delta S. And then entropy, and I'm going to write it in red. This is delta, and then this is delta H. Now, both play a role in, um, in determining whether a process is spontaneous. Now, you can have a spontaneous process, which means the reaction can go without there being any outside assistance. It can just keep going. Processes that are spontaneous in one direction, they are non-spontaneous in the reverse direction. Now, spontaneous don't mean fast. There are fast and slow reactions that are spontaneous. Now, non-spontaneous doesn't mean that the reaction is impossible. It just means that it's slow. Now, energy can be used sometimes to make reactions spontaneous that are otherwise would not be. Now, this is what happened. Now, think about temperature and pressure that affects spontaneity. Now, you can think about that with ice and with the different phases of water. So here you see ice is spontaneous for T is greater than 0 degrees Celsius. And then if you go the other way, it's spontaneous for T less than 0 degrees Celsius. Now, what can also happen is you can have reversible and irreversible processes. Now, with that, a reversible system, the system can change so that you can have the system and surroundings can be returned to the original state by having the exact uh, reversing the process. Now, you can do that. This maximizes work that is done by the system. Now, you can have irreversible processes. They can't be undone. That's just like breaking an egg. So once you break the egg, that's it. You can't pick the egg back up and put it back into the eggshell. Once it's broken, it's broken. Now, spontaneous processes, they are irreversible. Now, entropy can be thought of as the measurement of randomness in a system. It is a state function. So delta S is equal to S final minus S initial. It can be found by heat transfer of the surrounding at a given temperature. So delta S can equal to heat over temperature, and temperature can be constant. So entropy, delta S. Now, this brings us to the second law of thermodynamics. The entropy of the universe increases in any spontaneous process. The result is in this. So reversible is delta S of the universe is equal to delta S of the system plus delta S of the surroundings. It has to be equal to 0. If it's irreversible, delta S of the universe is equal to delta S of the system plus the surroundings. It has to be greater than 0. So this is the second law of thermodynamics. Now, when we talk about entropy on a molecular scale, we are talking about Boltzmann constant, and we'll get into that a little bit later. But gases is more so expanded. So two molecules start out side by side. What is the likelihood they end up together? So what they did was they have these gases in there. So one gas is in A at 1 atm, and then B is empty. Now what happens if you open up the stopcock? When you open it up, it's going to equal out. It's going to go zero point 0.5 and zero point 0.5 if you use 1 mole. Now, gases spontaneously expand to fill any given volume, and that's because the particles are random. Um, and what happens is you're going to have equal molecules or equal moles on each side. That is what's going to happen. Now, you can have thermodynamics, which is um, you can look at it from a statistical point of view, but it look at both properties. But what happened on the molecular scale? So what happened in a molecule? We use statistics in order to relate them. What we look at are these microstates, and there's a single possible arrangement of position and kinetic energy of those molecules. Now, we use Boltzmann use of that. Now, we use capital W to represent the number of microstates because there's so many of them. So we use that. Entropy is a measure of how many microstates are associated with a particular macroscopic state. So the connection between these two is x equal to k natural log of w. Make sure when you're going through these, you need to write down your equations and everything so that you can have them. So with this, entropy is a state function. The final value minus the initial value would give you an overall change. And in this case, an increase in the number of microstates results in a positive entropy change or more disorder. So this is it right here. K log of W final minus the initial. What you're going to get is a fraction involved. So that's the natural log of W final over W initial. So what else happened? You can have volume and temperature change on the system. If you increase the volume, there are more positions for the molecules. More microstates increase entropy. If you increase the temperature, your kinetic energy increases. This results in a greater distribution of molecular speeds. More kinetic energy, more microstates, more entropy. So if you got more in there, you're going to get more entropy because there's more room for randomness. So you have different types of motions when you deal with this. There are several types. You can have translational, you can have vibrational, or you can have rotational. Now, rotation of the molecules are about an axis. That's what you happen with that. So with vibrational, the motions are just within the molecules. Now, when you have translational, it's movement from one place to another. More atoms mean more microstates, more molecular motions. Now, how does that relate to, like you say, ice? Ice, water, liquid water, and then you have gas particles. And we'll talk about that in just a moment. Now, microstates increases with temperature, volume, and the number of independently moving molecules. So what do I mean by that? The number of independently moving molecules. All right. So freedom of motion. So let's think about this. You got entropy of a gas is greater than entropy of a liquid, which is greater than entropy of a solid. Entropy of a system increases for processes when gases form from either solids or liquids or solutions from solids, and then the number of gas molecules that increase from a chemical reaction. Because you think about a solid, those molecules are, as you see right there in the picture, are in place. And then when you got a liquid, they start interacting a little bit more. But then when you have water vapor or steam, those particles are so far apart to the point that they are interacting as their own individual particle. Now, this is where the third law of thermodynamics come in. The entropy of a pure crystalline substance at absolute zero is zero. So, if you consider all the atoms and molecules are in a perfect lattice at 0K, there would be only one microstate. So, in that case, S would basically be zero. Entropy is zero. So, on here we got tables that uses standard entropies. You can look at Appendix C in the back of your book. It have those standard entropies on there, the molar entropies and all of that. For your exam that you're going to have, what you're going to see is in the back of your book in Appendix C, you have delta H, delta G, and delta S. You can use Appendix C in the back of your book for your exam. And so this is just a chart. And these are references for different substances. So it's a more extensive list in the back of your book. Now, when you have entropy changes, you can have those for a reaction, and you calculate them the same way you calculate delta H. The sum of N, those are your coefficients, times S of your products minus the sum of your coefficient of delta S of your reactions. N and M are the coefficient in the balanced chemical equation. You will see on a later recording or an earlier recording how I worked that, and you have a problem like that on your exam. And I went over that on the written part extensively earlier. So make sure that you go over that and you remember this equation, and you have to take into account products minus reactant. Now, what else happened? Heat flows into and out of a system. Those changes to the entropy of those surroundings. Now, what we're going to do, what you're about to see is everything come together and actually relate everything. So you got Q surroundings over T is delta Q over delta Q of your system over T. You know, at constant pressure, Q of your system is simply delta H if the pressure is constant. So this is what happens in your surroundings. Now, when you do this, the universe is composed of system and surroundings. So you got delta S of the universe, you got the system and your surroundings. Now, if you're going to have a spontaneous process or a spontaneous reaction, delta S of the universe have to be greater than zero. Now, what's going to happen is when you do this, you will deal with spontaneity. So delta S of the universe is equal to systems and surroundings. Now, you got to substitute in entropy for the surroundings. When you multiply by negative T delta S, you see what you get is, and if you rearrange it, you would get the Gibbs free energy. So negative delta G is equal to delta H minus T delta S. So that is Gibbs free energy. Now, if delta G is negative, you got to remember this because you may see this on the exam. If delta G is negative, it's a forward reaction and it is spontaneous. If delta G is zero, it's at equilibrium. If delta G is positive, the reaction is non-spontaneous, but it's a spontaneous in the reverse direction. Now, just like you do delta S, delta H, you can do delta G the same way. So you can do that. That's still in Appendix C in the back of your book. This is free energy. This is free energy of formation. When you see the F, it's talking about formation. So you have those right there. and you use the same one because they are all state functions. Now, this chart is very important. You will see this on the test. Make sure that you know your signs when it comes to this. How the signs of delta H and delta S affect spontaneity. You got to know how entropy plays a part and how entropy plays a part. So you got to know the differences between both of them. How do they play a part? Now, let's go back to equilibrium for a second. Under any condition, standard or non-standard, the free energy change can be found this way. And make sure that when you're going through this, you need to write down all these equations, because if you write them down, you can remember them. So delta G is delta G of formation plus RT, natural log of Q. Y'all know K, Q, the same thing. Under standard conditions, you use 1 molar, so Q is equal to 1, and the natural log of Q is 0. That last term is going to drop out. Now, when that last term drops out, you get Q equal to K and delta G equals to 0. You got your equation that looks like this. Delta G RT natural log of K. Then when you have that, you can write delta gives free energy of formation of delta G is equal to negative RT log K. Or you can solve and find K is equal to e to the negative G over RT. So you can find that, and when you find that, you can do different types of reactions. Now, where is this really useful at? We talk about this actually in biochemistry, and this is one of the reactions I'm actually discussing with the class of forming ATP, and it goes to ADP plus P sub I. So you will see this again if you're taking biochemistry. So you will do a lot of this particular type of math also in biochem. So don't forget it. Don't put it on the back burner. You will come back to it. You will see it a little bit in organic. You will see it a lot more in biochem.